Hi everyone, and welcome to my talk on NumS, a scalable numeric array library for the cloud. The core objective of NumS is to improve the runtime of multi-dimensional array programs in Python and enable Python's scientific computing community to analyze and model larger datasets. An ideal Python solution seamlessly parallelizes and scales a NumPy-like array API, allowing scientists and statisticians to leverage their existing programming knowledge without having to learn new skills. To achieve this ideal solution, we identify three key problems that must be solved. First, to effectively parallelize NumPy-like code, we must determine dependencies between operations and then concurrently execute any independent operations. Second, we need to avoid high overheads from parallelization. For example, the naive approach of sending one RPC per element-wise array operation poses untenable overheads. Third, to scale array operations on distributed memory, we must both avoid high network overheads and load balance the data among the different nodes. Here are some solutions that solve some of the problems we've presented so far. First, we have NumPy, which primarily is serially executing. It provides shared memory parallelism for basic linear algebra operations via the system's BLAS implementation. Second, existing single program, multiple data, distributed memory solutions such as MPI present Python users with an unfamiliar programming model. Third, block-partitioned Python array libraries such as Dask arrays rely on task graph scheduling heuristics optimized for general workloads instead of array operations. To our knowledge, none of these solutions simultaneously solves all three of these problems. We therefore developed NumS, a numerical cloud computing system that compiles NumPy to optimize distributed memory code at runtime. The components of NumS and its interactions with external processes are captured by this data flow diagram. The user interacts with the NumPy API, which is built atop the array application. The array application produces block arrays, which can be operated on in the same fashion as NumPy's ND arrays. The block arrays can be converted to graph arrays for optimized scheduling. Block-level operations are then submitted to the compute manager, which are sent to the distributed system interface. The system interface then invokes RPCs on the distributed system, which carry out the actual computations. We now turn to our solution to the three key problems we solve with NumS. First, we solve problem 1 by exposing a NumPy-compatible array abstraction defined in terms of futures, allowing the scheduler to see the computation graph in advance and parallelize execution. In NumS, arrays are comprised of futures, and their operations are carried out as promises. This captures exactly the data dependencies required to compute each block in the output array, allowing for concurrent execution of independent operations within and between output blocks. Whenever an array access is triggered, high-level operations on the resulting new array are captured as low-level block operations. This dynamically constructs a task graph, whereby dependent tasks are queued and independent tasks are executed concurrently by the distributed system, and in this case, the distributed system is Ray. For our solution to problem number 2, we solve problem number 2 by coarsening operations by partitioning arrays into a grid of blocks and performing array operations blockwise rather than element-wise. The block array type is the backbone of NumS. It provides an implementation of all array operations in terms of blocks. A block array has a shape, which carries the same meaning as a NumPy ND array shape. Here we present a block that has shape 4 by 6. Each cell in this table specifies the array index, used to access the corresponding value within the array. The larger cells in this table denote the block partitioning of the array. The block shape property indicates the shape of each block. In this case, the block shape is given as 2 by 2. Thus, NumS will try to partition the array blocks into shapes of 2 by 2. We may end up with blocks that have fewer entries in the specified block shape if the array shape is not divisible by the given block shape. Finally, the grid shape of a block array indicates the layout structure grid used to organize blocks. The grid index or entry provides a way to access blocks of array elements within a block array. To provide some context about the way block arrays are constructed and represented with array backend, we provide a simplified example of a read operation. In this example, we have a 2-node array cluster on which NumS is operating. NumS code executes on array driver. The read operation immediately generates an object reference. So long as the object references are in scope, array will ensure the object associated with the reference remains in at least one store. The data in S3 is two-dimensional and is partitioned into 2 blocks along the first axis. And the S3 database is denoted by the storage icon here. So to begin, NumS will issue a read RPC on worker nodes. It then reads data from S3 in parallel and caches the data locally on each node. Finally, the returned object references are referenced in the driver application. Note again that so long as the object references are referenced on the driver node, the corresponding objects are guaranteed to exist somewhere on the cluster. To demonstrate the NumS API, consider a basic implementation of logistic regression optimized using Newton's method. NumS loads X and Y and initializes beta concurrently as block-partitioned arrays. The block of code highlighted executes in parallel. All operations are executed blockwise, providing intra as well as inter-operation parallelism. The termination condition is executed concurrently as well. Here, the driver process blocks until the resulting Boolean value is evaluated, allowing the driver process to branch. We note here that, while this expression blocks, it only depends on G, not mu, H, or beta. As soon as a termination condition is evaluated, the next loop executes, providing partial parallelism between independent operations between each instance of the loop. Finally, to solve the third and final problem, we design a novel scheduler called Cyclic Random Tree Search, abbreviated as CRTS throughout the rest of the talk. CRTS combines a traditional block cyclic data layout with an objective-based operation scheduler. The block cyclic data layout used in CRTS can be described as follows. We represent n-dimensional arrays as structured grids of blocks, as previously defined. We additionally represent a cluster as a structured grid of nodes. We then determine the node on which each block resides by cycling over available nodes along each axis. This design strikes a balance between data load and data locality, which provides a solution for zero communication element-wise operations and enhanced data locality for basic linear algebra operations. We now turn to a description of our scheduling optimizer. Our optimizer is comprised of 4 primary components. First, we have a cluster state, which is used to estimate memory and network load on each node by using the size of every array. Second, we have an objective, which places operations to minimize maximum memory load and network load over all nodes. This is very similar to the objective of traditional load balancing. Third, we have a computation state, which is represented as an array of graphs data structure on which we perform the computations. This is the graph array mentioned previously. Finally, we have Cyclic Random Tree Search, or CRTS, an iterative algorithm that places a single operation per iteration according to the objective and updates both the cluster state and the computation state. This diagram illustrates the procedure NumS carries out to optimize placement of expensive operations. We first convert block arrays to arrays of graphs, called graph arrays, consisting of a single leaf node denoted as circles. Operations are performed on collections of graph arrays, growing the computation graph within the output graph array. The optimizer then schedules computations on nodes according to our objective, which minimizes maximum memory and network load over all nodes. The resulting graph array consisting of leafs is converted back to a block array. Digging deeper into the optimizer itself, consider a tensor dot between two matrices A and B. The operation has three representations. It has the syntactic representation. It also has a block array representation, which decomposes the arrays into blocks. And finally, the graph array representation, which represents the tensor dot operation as a computation graph with frontier nodes. Frontier nodes are nodes on which operations can be performed. The optimizer proceeds by randomly sampling a frontier node. The sampled frontier node is then scheduled on a cluster device. We sample to minimize the cost of running the optimizer at runtime and reduce the likelihood of scheduling inefficiencies due to deterministic enumeration of frontier nodes. The optimizer schedules the operation on the device that minimizes maximum network load and memory load on the cluster. And this behavior is captured by the objective, which we have here. The objective quantifies the cost of scheduling decision I from cluster state S. In this example, the optimal choice is to schedule on device 1. Looking closer at the objective, we see that M is the vector of memory load on each node, I is the vector of input load on each node, and O is a vector of output load on each node. The infinity norm computes the maximum value of a vector. So what we're really doing here is just computing the maximum value of each of these vectors and summing them up. We now turn to the result of our empirical analysis of NumS. To begin, we ask whether CRTS improves performance. This plot shows memory and network load collected over the training of the same logistic regression model. Each column of plots corresponds to a different scheduler, and each line in each plot corresponds to the load of each node over time. The first is Ray's default scheduler, which does well to maintain data locality. Second, we use a block cyclic data layout for basic linear algebra operations. This fails under certain circumstances and causes an imbalance in memory and network load per node. Finally, CRTS is able to balance both memory and network load, as is evident by the clustering of line plots over time. The memory load we do see in CRTS is due to the dataset and the output of RPCs. The high network in at the beginning of the computation is data being read in from S3, which decreases slowly as the computation reaches its end. We show here the execution time in seconds of the various scheduling algorithms we tested. The only scheduler that can scale to 1 terabyte for this specific workload on these specific resources is CRTS. Next, we answer the question, how well does NumS scale? All the experiments we perform in this section are weak scaling experiments. We show that NumS scales perfectly all the element-wise operations that can be found in the NumPy API. This is due to our use of the block cyclic data layout. For this experiment, we double the amount of work and number of workers until 512 cores on 16 nodes are used. Also, NumS exhibits similar scaling properties for data sampling. We also provide scaling results for two major algorithms, logistic regression and QR decomposition. On the left, we measure the throughput of 10 iterations of logistic regression. We scale near perfectly until 16 nodes. At 16 nodes, the cost of multiple reduction operations at 2.5 gigabytes per second decreases throughput. On the right, our implementation of QR decomposition scales near perfectly. Next, we experimentally show that NumS is competitive and outperforms related solutions on several key benchmarks. We compare our logistic regression and QR decomposition implementation to Dask's. Both implementations use the same algorithm. The plot on the left shows that our logistic regression implementation can be up to 20 times faster than Dask's. On the right, our QR decomposition implementation is competitive with Dask's highly optimized implementation. We also compare our logistic regression and QR decomposition implementation to Spark's MLlib. Spark's MLlib does not support the Newton optimizer for logistic regression, and its QR decomposition implementation is different than Dask's. We therefore use a different set of algorithms to provide a fair comparison to Spark's MLlib. Also, because Spark's algorithms are sensitive to the number of partitions, we tune the number of partitions for each dataset size to achieve the best performance for both Spark and NumS. At 1 terabyte, our logistic regression and QR decomposition implementations are 2 to 3 times faster than Spark's. Next, we answer the question, can NumS run on the GPU? Here we show that NumS is able to run on the GPU with a re-implementation of the system layer using CuPy and NVIDIA's collective communication library. The same NumS code provides a significant speedup over CuPy alone and is able to scale to 40 gigabytes on 2 nodes. The results of this experiment show that NumS optimizer converges to synchronous model and data parallelism, eliminating the need to write specialized parallel algorithms to train deep neural networks. Both experiments are on the multi-layer perceptron. In the model parallel case, the hidden layer size is increased and partitioned into 4 blocks. Any operations performed on the hidden layer are then parallelized. In the data parallel case, data is partitioned row-wise into 4 blocks. The model's hidden layer is smaller than the dataset size, so our CRTS scheduler broadcasts the model to devices on which the blocks of data are located. This achieves the ubiquitous synchronous data parallel training procedure that is often used to parallelize deep neural networks trained with stochastic gradient descent. Finally, we show that NumS can be used to solve real data science problems with an end-to-end benchmark on the Higgs boson machine learning challenge. We compare Panda's load time, scikit-learn's train time, and scikit-learn's prediction time to NumS's. We show an overall 7x speedup on a single node and 10x speedup on 2 nodes. That covers all of our experiments, and here we'll just show how you can use NumS. You can simply run pip install NumS, and NumS has been tested on Python 3.7, 3.8, and 3.9. NumS runs on the latest versions of Ray, and that's 1.3 as of this talk. And it also runs on Windows. Some of the features of NumS include full support for array assignment, broadcasting, and basic operations, I/O support for distributed file systems, S3 and CSV files, prepackaged support for generalized linear models, experimental integration with Modin, which is a data frames project, and XGBoost, which is a tree-based models project. And we're continuously updating the NumPy API, and we have several contributions from several great Berkeley undergrads. For future work, we are hoping to integrate our research on GPU support, add support for sparse arrays, continue improving memory and runtime performance, and of course continuing to expand the API coverage, and continuing to add support for linear algebra and machine learning. This includes LU decomposition, Cholesky decomposition, matrix inversion, and multi-class logistic regression, which are all currently in the works. And that concludes my talk, and thank you. Please feel free to email me or anyone on the NumS team with questions.